Hi, this is Charles Hoskinson broadcasting live from warm, sunny Colorado. Always warm, always sunny, sometimes Colorado. Today is August 29th, 2023, and we get to talk about aliens, or at least spherules, from different places today. So many of you know I finance a lot of different interesting things. For example, the Hoskinson Center for Formal Mathematics, or obviously a lot of the work that we do in synthetic biology and regenerative medicine. But I'm also very interested in astronomy. And in particular, I'm interested in changing narratives. So there's a project called the Galileo Project that's led by Avi Loeb, who's out of Harvard University. And he took a huge risk in that he was one of the few astronomers, astrophysicists, who had the courage to take a stand and start talking about what most people enter astronomy and astrophysics about, which is the existence of extraterrestrial life. It's kind of a bizarre concept that we're this tiny blue marble in the middle of this gargantuan ocean, and somehow, some way, we're only allowed to talk about things that are deterministic, mechanistic, effectively dead, and we can't think of this idea of intelligent life. So Avi had the courage to talk about things like Oumuamua, for example, and also write a lot of really interesting papers about how the universe could be populated with intelligent life and the things we should look out for. So I was always a fan of his work, and I saw him on Joe Rogan and saw him on Lex Friedman, and we both share friendship with Lex Friedman. So eventually, when he wanted some financing to go to Papua New Guinea and actually launch an expedition to retrieve something that had fallen into the ocean in 2014 that had a high probability of being an anomaly, I said, all right, well, let me take a look at the science. And so I had several calls with them, and we kind of talked around how we would do an expedition, the types of people that would be needed, the technologies that would need to be put into place. And then eventually we converged to an understanding, and I went ahead and financed it, and we went out there. So between June 14th to June 28th this year, we were 60 miles off the coast of Manus Island, in the middle of the Pacific Ocean, so far out you couldn't see anything at all. It was just ocean every place you look, on a catamaran made of aluminum. Does this 24 hours a day, 7 days a week. Get used to the sea legs. We were able to deploy a magnetic sled, drag it behind the ship over a large search area, and we recovered spherules. Many spherules, over 700 of them, ranging in diameter from 0.05 to about 1.3 millimeters in size. So smaller than a human hair. So anyway, like all good academics, we wrote a paper together. First time I ever wrote a paper out of Harvard, but first time for everything. And the paper is now public. It is 44 pages long, and I figured I'd cover a few details with you guys. So the paper is titled Discovery of Spherules of Likely Extrasolar Composition in the Pacific Ocean of the CNES NEOS 2014-01-08. So January 8th, 2014. And we refer to it as IM1. And you see a lot of different authors from Berkeley, from the PNG University of Technology. And by the way, special thanks to them. PNG has just been great in this entire process. And then obviously a lot of Harvard authors as well. And then there's me. Okay, abstract. We have conducted an extensive towed magnetic sled survey during the period of the 14th to 28th of June over the seafloor about 85 kilometers north of Manus Island, Papua New Guinea, and found about 700 spherules of diameter 0.05 to 1.3 millimeters in our samples, of which 57 were analyzed so far, which, by the way, we're analyzing more. Approximately 0.26 square kilometers of seafloor was sampled, and the survey centered around a calculated path of the asteroid or interstellar object, with control areas north and south of that part. The spherules significantly concentrated along the expected meteor path were retrieved from the seafloor depths ranging about 1.5 to 2.2 kilometers. So first, it's important to understand when we dropped this sled, and this is what the sled looked like, this guy right here. When we dropped it behind the ship, it actually took over an hour to reach the seafloor because the seafloor is 2 kilometers down. So that's 6,000 meters. Imagine that. That's 6,000 feet, more than 6,000 feet, 2,000 meters. That's just an extraordinary amount of depth. So then we did mass spectrometry of the 47 spherules. And basically, the long and short is this line right here. The unique spherules show an excess of beryllium, lanthanum, and uranium by up to 3 orders of magnitude relative to the solar system standard of CI chondrites. And so we call it Balau. These Balau type spherules, never seen before, also have very low refractory siderophile elements such as, where are we at? Rubidium. Yeah, volatile elements such as magnesium, zinc, and lead are depleted as expected from evaporative losses during a meteor outburst. In addition, mass-dependent variations, and they would go through the isotopal analysis. So it's a long paper, and it's a proper scientific paper, and we kind of talk about how we collected everything. So it's important to understand we sampled not just, and right down here is the sampling area, so all these different paths that we took. So these squiggly lines are actually the ship path as we were going through for those 2 weeks. And this is kind of the heat map of where the density of spherules are. So we took controls that were far away from where we thought the meteor landed so that we could compare those and their isotopes and their analysis to what was inside the search area. And so we did a lot of analysis of it, and then we actually show the different analysis. And we kind of broke it into 4 groups. So these are electron microscope images of the spherules. So, the electron microprobe image of spherule S21. So that's a 3-part. So these are actually 3 spherules that melted off the skin of the object, and they merged together, and they were able to melt it and take a look and see the different elements in it, like carbon, oxygen, magnesium, aluminum, silicon. You'll expect to see a lot of silicon in these types of samples because that's contamination from the sea floor. But the D type are the interesting ones here. So, yeah, the D type spherules, we mentioned it up here in the paper. The imaging morphology, quad element analysis, sample and location. They moved some things in the paper around. They were working on this late. Yeah, refer to these new type of differentiated spherules as D-type spherules. These have never been described in the cosmic spheral literature. There are 2 subtypes of the D-differentiated spherules. We call the subtypes low lanthanum and the Balau, the distinct elemental patterns in Figure 10. And then Figure 10 is it's Table 10, Figure 9. Yeah, 10. You can see the different abundances. So this is the background of what you would expect to see in the solar system. And then these are elements down here. So if you zoom in, you can see different elemental types. So, for example, you have titanium and uranium and lanthanum. And this is 10 times the abundance of what you'd expect to see in the solar system, 100 times the abundance, 1,000 times the abundance, 1/10 the abundance, 1/1000th, 1/10,000th. And you can see the siderophile elements. Stuff is quite low, and you wouldn't expect that. And then up here with uranium and beryllium, it's quite high. So it's very unusual. And then the low type has different characteristics. So it's an active scientific project. It's been submitted to a journal that specializes in oceanography. And because it was recovered, and it's novel to recover these types of things from the ocean. And then there's going to be some follow-up papers that are more on the astrophysics and astronomy side as we analyze more of the samples, because there's analysis happening at Berkeley, Harvard, and in Berlin at the same time. But it's really impressive science, and there's some really cool things that are inside the paper. But the conclusion is the fun part. Conclusions. The magnetic sled survey around IM1's path during the period of the 14th to 28th of June discovered about 700 spherules of the diameter through 26 runs. Those runs, by the way, were every 8 hours. We didn't sleep. We just woke people up and said, go outside and scrape stuff off the sleds. The spatial distribution of these spherules is significantly concentrated along the bolide path, as shown in Figure 4. So, and the Figure 4 is up there. Mass spectrometry measurements at Spherules I1 show a high enrichment of beryllium, lanthanum, and uranium, which with extremely strong enrichment of refractory lithophile elements, very low refractory siderophile elements such as rubidium, volatile elements such as magnesium, zinc, lead were mostly lost in the evaporation. But really what we can say is definitively, looking through the paper down here, here we go. This is the money shot. You always have a money shot. The Bilal abundance pattern suggests that IM1 may have originated from a highly differentiated crust of a planet with an iron core outside the solar system. In that case, IM1's high speed of 60 kilometers per second, the local standard of rest in the Milky Way galaxy, and an extremely large number of similar objects per star, and statistically for the population of natural interstellar objects it represents, are challenging to explain by common dynamical processes. The Bilal overabundance of heavy elements could perhaps instead have originated from an process enrichment and fragmentation of ejecta from a core collapse supernova or neutron star mergers. However, the Bilal pattern also displays S process enrichment, which must have a separate origin, such as an asymptotic giant branch stars, and they give some more citations. Another possibility is that this unfamiliar abundance pattern may reflect an extraterrestrial technological origin. These interpretations will be considered critically along with additional results in the spheral analysis. So basically, we found something where the way it looks, when you really start breaking down the composition with some pretty sophisticated instruments, it's probably not from our solar system, which is why you can say with probably a good, straight face that it's extrasolar. The issue is we don't have enough knowledge yet from what we found to be able to say that it's extraterrestrial or it came from a collapsed star or from a core of a different type of planet. But this is, I think, the first extrasolar object definitively recovered on Earth as a spherules. The other cool thing is that this pattern right here, we've been able with these to isolate a bit basically where the big pieces landed. The big pieces, you can do a different type of analysis because there'll be enough material that we could definitively say whether this is of a natural origin or an artificial origin. And we mentioned a lot about crystallized magma and these types of things of how it could come from a core of a planet. But it's an amazing piece of science, and an enormous amount of work went into this, especially with Stein Jacobson. He sat down for day after day after day, patiently preparing the samples, of which there's hundreds of them. I mean, this looks big, down here when you take a look at the sphere, but the reality is that this is smaller than the size of a human hair. It's very hard to see with the naked eye, and he had to prepare this and actually get the compositions out of it. This is something that you get only when you've been doing it for a very, very long time. And he's professor at the Department of Earth and Planetary Sciences at Harvard. You don't get to be a professor at Harvard unless you're a rock star in your particular field. So it was incredibly impressive, the work that he did. The graduate students on the paper did as well. And, and then on the salvage team, Art Wright is kind of a living legend on his own. He's 87 years old. He's a retired Navy captain. And he's the guy the Navy called up to find Russian nuclear subs and all kinds of things. If you kind of Google Project Azuria, he was the guy there. And some young people too, like Amir Siraj, who was Avi's graduate student. So this was an all-star team of people. JJ, for example, he didn't just come along. He actually ran the lab. So all these samples that you see, the collection and how we organize things and the tubes that we put them in. So right here's Avi's blog. See the team right there. And there's JJ cleaning the sled. We figured out that the vacuum cleaner was the best way of doing it. And then down here, that's Stein, and that's one of the devices that he used for the mass spectrometry. And then if you go down, you can see us kind of taking a look at some monitors. These are what they look like actually inside the spherules. Beautiful structure. There's me. This was late at night. We're exhausted as hell. That's Ryan Weed. He's actually an Air Force guy. He came along and he's got a PhD in nuclear physics and he's an expert in antimatter propulsion. And there's Jeff Wynn. Jeff is a very famous geologist at USGS. But that's Art Wright right there, that old guy, 87 years old, and he can kick all of our asses because he's tough as nails. He graduated from the Naval Academy in the 1950s, and I think his first assignment was on a diesel carrier, just to give you a sense of how old he is, and he's still sharp as hell. So it was very good science. It was a great expedition. We learned an enormous amount, and what we're going to do is try to figure out how to get the big pieces, and then we can definitively say if this is a natural or an artificial object. But regardless, no one's ever really done anything like this quickly and in this way, and brought together such a great team of people from Harvard, UC Berkeley, the Brunker Corporation, the University of Technology of Papua New Guinea. There's just so many amazing people that came together so quickly, and we got a great result. And literally, we did it with this little sled right here that we dragged behind a ship made of aluminum in the middle of the ocean for 2 weeks, and had to sail this thing all the way to the ground. Now, it had a camera on it, but we didn't get a real-time feed because you'd need to put fiber optic on the sled, and we didn't have a big enough winch for that. So it meant this guy right here, Art, just by eyeballing it, know whether that's sailing and it's floating or if it's on the sea floor, just line tension and eyeballing it. And he actually got it right. And we figured out within about 2 days how to do that. So it was so much fun being part of this and participating in it. And it was so much fun actually being able to do some good science. And I really enjoy the peer review process. We've written 180 papers on the IO side with 168 academics, and about more than half of them have gone through rigorous peer review with over 10,000 citations. So we're not afraid of that. And it's going to be fun to see what the community has to say about the Palau Spherules and where we go from them. The next expedition would require side scan sonar and robots. These are called ROVs, remote operated vehicles, and a different type of ship and a different type of camera system, potentially submersibles as well, because we wouldn't be looking for little spherules. We'd actually be looking for large pieces of the object, which are far more exciting to recover. But science is done in stages, and the first stage is to build an all-star team and then get a confirmation that there's something interesting, go through the peer review process to get a much better understanding of what exactly you're dealing with. And then the next step is to actually go and retrieve the big stuff and then see what you get from that big stuff. So we'll get it done one way or the other. And I hope this inspires a lot of people around the world who are interested in astronomy or astrophysics, who also care about extraterrestrial stuff and who care about intelligent life in the universe or the search for it, to be inspired to do similar types of research. One of the most disheartening things throughout this entire process is there were people at Arizona State and other universities who said, we no longer even want to peer review Avi Loeb's papers, which is an extraordinary statement. We did some good science. We said what we were going to do. We went and did it. We recovered actual samples. We analyzed the samples with the best people in the world at facilities at Harvard, which is pretty hard to argue with. These are facilities that aren't even the millions, and they're tens to hundreds of millions of dollars worth of equipment. And we wrote a 44-page paper, which has a lot of rigorous stuff inside of it and a lot of explanations of things. We still have the samples. They're there, and they're being independently analyzed by other labs as well, and additional papers are being written. There's an obligation, I imagine, in the academic community to take that seriously and do things, not because it's inconvenient to their beliefs, but because that's how science should be done. And my hope is that we can kind of break through and make some progress there. Regardless, finding stuff in the middle of the ocean is an art. It's incredibly hard to do, and it was a lot of work with everybody who was involved. And I was real proud to be part of it, and it was really awesome to see how everybody came together and became a team. We all kind of knew each other when we showed up, but we really knew each other by the time we left, because 2 weeks in the ocean is real tough for anybody who's been out in the deep ocean with people for a while. So I figured I'd let all of you know. Next steps are we'll continue the peer review process, plan the next expedition. Netflix shot a documentary of it. They were on board the ship with us. It's going to be a 90-minute feature, and it's being done by Jason Cohen. He's a great director. And then we'll, get some more popularity as time goes through, publicity. For example, we're probably going to do Joe Rogan or something like that. But we have to kind of get the science out of the way first. And interpret the results and go through the entire process. If you're interested in the paper itself to read it, I've put a link to it in the show notes, but I will also put a link here. There you go. So you guys have it. You can just freeze frame and type it in. Open paper. Feel free to share it. Feel free to read it and send all your questions to Avi and team. So thank you all for listening. This one was a fun one, and it's a little side quest. We got it done. But it is our commitment to good science. Cheers, everyone.